our planet is heating, right? So we look at the temperatures over the past 100 years is rising steadily. We can correlate the rising in temperature with the cumulative CO2 emission over the past decade. And we know that the temperature of the planet's rising has to do with a so-called greenhouse effect. And so having more CO2 or greenhouse in the atmosphere, we can essentially, the planet, the Earth, can absorb more of the heat. And this has to do with greenhouse gases can absorb essentially the infrared, the heat emitted from the planet. And this is a really combination of the work through Wayne and Tito's work. So essentially, we know greenhouse gases like CO2, like methane and water, absorb far infrared range, allowed Earth to be able to keep more of the heat, otherwise it would be emitted away from the planet. And so if you want to essentially keep or maintain the temperature rise to be 2 degrees or less than 2 degrees in the coming decades, we need to significantly decrease our CO2 emission. And we need to do so very rapidly in the coming decade. We emit CO2 mainly from 4 sectors: agriculture, our use for our industry, energy use in transportation, and as well as energy use in our buildings, and roughly, divided equally in these 4 sectors. Essentially, we face the challenges of decarbonizing, how we essentially reduce our CO2 emission from our transportation, how do we decarbonize heat and electricity from our buildings, how do we decarbonize how we make materials, such as steel or concrete, and then how do we decarbonize agriculture sector. So let's look at some numbers. For example, let's say, what's the weight of CO2 emitted in the lifetime of internal combustion engine vehicle? Right? Let's say an average car is 4,000 pounds. And feel free to unmute, right? So what do you think is the lifetime of the weight of CO2 emission for a car? Is that 1% of the car weight, 10%, 100%, 10 times, or 100 times? Any thoughts?
I think it's 100% of the weight.
Good guess, good guess. And on average, the CO2 emission is about 10 or 20 times of the car weight. In addition, we make ammonia for agriculture, and that's really important for sustain essentially the population and population growth. And ammonia making consume roughly 1% of our energy globally and emits 1.4% of total global emission. We make a lot of metals, and most of the metal we make is really iron, right, for steel making. And then the rest of the metals are essentially we have many different kind of metals we mine, right? And some are really critical materials, right? And they are much smaller in volume or weight relative to iron, right? So to decarbonize, the heat associated with mining and material or metal making is critical. Iron making or steel making is already pretty clean in terms of CO2 emission. We're at 2.3 ton of CO2 per ton of steel. Aluminum, as through electrolysis, is at 17 ton of CO2 per ton of aluminum. If you look at gold or platinum, we're at orders magnitude more tons of CO2 per ton of metal mined. Right? And this is surprising to me when I heard these numbers. Any guesses why mining gold or platinum would generate so much CO2?
The concentration in the earth is much lower.
Exactly, right? So concentration, essentially the ore, right? Or where we mine gold or platinum is on the level of ppm, right? Orders magnitude. Essentially the concentration roughly scale with essentially the energy intensity or CO2 emitted, right? So even though gold or platinum or precious metal is a tiny fraction of our total metal mined, and today cumulatively they contribute to roughly 0.5% of total global CO2 emission today. So we face tremendous challenges in these sectors to reduce CO2 emission, right? We have also a wonderful opportunity. We have low-cost electricity from solar wind. We can essentially store the energy and electrify our transportation, especially for light-duty vehicles. We can utilize electricity to generate energy carriers, right? So that we can decarbonize heat for industrial sector, for how we make materials for our buildings. And we can decarbonize how we make metals and recycle plastic, because it's all making concrete. And we can utilize essentially electricity or electricity associated hydrogen carriers to do carbon capture and carbon sequestration. Electrochemistry play a central role in developing essentially processes so that we can displace fossil fuel and generate new technologies that based on water, based on electricity, based on nitrogen and CO2. Right. So we can think of, we have different type of batteries, lithium ion, beyond lithium ion, metal air, metal valent batteries, sodium ion. So the number of batteries, the names can be quite extensive. We also have redox flow batteries. We have fuel cells, electrolytic cells, a different type of cells to make metals, to make chemicals, as well as these electrolytic cells to capture CO2, convert CO2 to chemicals and fuels. And they can be, very overwhelming and confusing. Right? And what I like to advocate is following, that if we understand a few fundamental processes, right? So let's say for electrochemical devices, the core process is the electron-ion transfer process at the electrified interface. Right? So essentially controlling how the electron and ion transfer at this interface will determine the power and the energy, as well as the lifetime and often the safety of a given device. And the rate and the stability of this interface can be toned by the electronic structure of the solids, as well as by the molecular local environment of the liquid or the solid or polymers for the ion conducting phase. And of course, how we control the local environment around ions also influence how ions transport within the ion conducting or mixed electronic ion conducting media. Right? So if essentially, regardless what devices or technology we work on, if we can understand these few processes, we can essentially develop improved understanding and develop novel technologies, regardless whether it's batteries, fuel cells, or electrolytic cells. So I want to use a few examples to advocate the needs of fundamental understanding and apply fundamental understanding to address, for example, bottleneck challenges. And this is how we frame our research. We frame our research in terms of problem-centric focus. For example, if we think of development of fuels or chemicals, right? And so we have electricity. We want to store electricity by, storing the electrons in water, by activating water, CO2, nitrogen, or metal oxide to generate energy carriers like hydrogen, metal, or energy carriers, hydrogen-containing carriers such as ammonia or small hydrocarbon molecules. And during this process, we have oxygen evolution, regardless what electrolyte we may use, regardless of what molecules we're trying to activate. And during this step, oxygen evolution is one rate limiting step that affecting or limiting our efficiency of such conversion. So we focus on, for example, problems or reactions that just bottleneck in order to make a given technology viable. Right? So once we have the energy carriers, we can utilize them, convert them to heat directly, or we can combine them with oxygen in fuel cells or metal air batteries, and then regenerate electricity and the molecules in equilibrium at ambient conditions. And during this step, oxygen reduction is sluggish, also limiting the efficiency. Right? Not only we have the challenges with oxygen redox being slow and limiting the efficiency of such process, if we go beyond hydrogen, activation of CO2, activation of nitrogen further decrease our efficiency and rendering very low efficiency of the chemical transformation. And that is one of the focus point for our research. How do we develop either the surfaces, right, through electronic structure design of the surfaces? How do we design molecules at electrified interface so we can increase the rate of the reactions? Right. Just for an example, lithium-ion batteries are very efficient. They're at, even on the device level at 90 plus or 95% greater. In contrast, for such a cycle, even with hydrogen as the energy carrier, we're looking at round-trip efficiency around 50 or 60%, and therefore is very important for us to increase efficiency to make such devices more competitive. So we want to essentially design the catalyst surface so that we can lower the barriers of chemical transformation, right? So by interacting essentially the molecules with the surfaces so that we weaken the internal interactions, facilitating the making and breaking of new bonds. And this is the essence of catalysis. And we utilize two different approaches. One is through tuning of surface electronic structure to changes in covalent interactions, for example, absorption of oxygen, absorption of hydrogen on surface, and changes the binding of surface intermediates and influence the thermodynamic barrier. And through the BEP relationship or the linear free energy relationship, we can correlate the thermodynamic barrier to the kinetic barrier. Right, so lowering the thermodynamic barrier correspondingly will lower the kinetic barrier, and through which we can essentially develop electronic structure-based descriptors to tone catalytic activity. And more recently, we note that tuning the non-covalent interactions, for example, the hydrogen bond, for example, for reactions involving proton-coupled or decoupled electron transfer, it can play also a very important role in influencing the rate of the reactions through orders magnitude. And this is really exciting and a lot of unknowns. So how do we understand and tune the salvation environment at the electrified interface by varying the electrolyte, by varying the operating conditions, so we can facilitate the rate of the reactions through these non-covalent interactions. So we're going to begin with the first, how do we tune the covalent interactions? The basic idea is that we can control the absorption and desorption of oxidizing species or reducing species by essentially moving, let's say, electron from the D states to the oxygen P states among absorption of oxidizing species. And the driving force for this absorption would decrease if we go to later transition metal, where we go to a transition metal with higher oxidation state. On the other hand, if we absorb a reducing species, we're essentially transferring an electron from oxygen P band to the D states, and that driving force increases as we go to the late transition metal, where we go to a higher oxidation state. And this is basically the correlation between the changes in electronic structure and the changes in the binding energy. And so utilizing this general concept, one can correlate the experimentally measured, let's say, surface exchange kinetics for oxygen converting to O2 minus or O2 minus converting to molecular oxygen, and correlate this rate of the reaction with computed oxygen P band center relative to the Fermi level. right? Essentially, is you can compute the centroid of oxygen p band relative to the Fermi level, which is related to top of the valence band for transition metal, or essentially the Fermi level, and is bound by the filling of the d states and the position of the d states. And you can see from the central graph that as we go from lanthanum manganite to, let's say, barium, strontium, cobalt, iron oxide, the rate of the reaction can be increased by 6 order magnitude. Right. So through this correlation, one may say that oxygen p band center alone is a major descriptor that can tune the rate of such reactions. And similarly, such a descriptor can also increase the rate of oxygen evolution from in basic solution from hydroxide ions to molecular oxygen for the series of cobalt perovskites from lanthanum cobaltite to all the way to A-site or 2+ substituted A-site double perovskites. Considering TOEFL slope of 60 millivolts, we're looking at roughly 2 or 3 order of magnitude of increase for the OER catalytic activity. Right? So this essentially is a very simple empirical correlation. Right? So you correlate the computed oxygen p band center with experimental measured catalytic activity. We later on also measured oxygen p band center in bulk using X-ray absorption spectroscopy, also used X-ray emission spectroscopy, and also established and confirmed this correlation. One can also argue this is bulk p band center is not surface, and we can also show that through DFT and through measurement, the surface oxygen p band center also correlate with the bulk oxygen p band center. Right? So we can essentially utilize such a concept to further design what we can do in terms of changing the A site or B site to further tune the activity and sometimes the stability of the surfaces. One example is, let's look at, let's say, the cobalt perovskite. So we can substitute, let's say, 3+ ions into the A site. Right? And you can choose a different type of 3+ A-side ions, right? So bismuth 3+ is the most acidic. And this would pull essentially the electron density from oxygen, right, away from the cobalt ion. This would in turn will give a different covalency between cobalt and oxygen. And utilizing bismuth strontium cobaltite, we note is really the highest OER activity for the cobalt perovskites, and also in terms of oxides normalized per surface area. And this has to do with fine-tuning of the so-called inductive effect and through A-site tuning of modifying cobalt-oxygen covalency, and that we can allow to tune the right or optimize binding of different species in order to oxidize water to generate molecular oxygen. Right, so really tuning of decoupling of the D states, oxygen p band, and the covalency through this inductive tuning by choosing the most acidic A-site ions. So over the past decade or so, we have been essentially developing this so-called descriptor-centered approach, right? Relating electronic structure of oxides, looking at oxygen p band center relative Fermi level, and to the binding of reaction intermediates. We can also relate this electronic structure stabilization of oxygen p band relative to the Fermi level to the stability of the material, such as stability against dissolution of ions, right? And also stability of the surfaces reacting with, let's say, CO2 and water, and through which we can utilize essentially electronic structure to develop optimized activity and stability. Right? And over time, we can essentially go beyond one particular reaction, let's say oxygen evolution. We can correlate the covalency or correlate the electronic structure to a number of reactions, such as CO oxidation. Right? CO oxidation also requires a tuning of surface oxygen site in order to optimize the activity as well as NO oxidation to NO2, right? So remove NO is a really critical challenge in our NOx emission or for environmental challenges, right, associated with internal combustion engine. And it turned out tuning the metal oxygen P-band center can influence the development of more active oxygen site for NO oxidation to NO2. Right. So we develop really an approach that instead of studying different reactions independently, and we utilize a holistic approach that tuning really the active sites or binding of the metal sites, and as well as tuning the oxygen sites that make the oxygen site to have also the right binding energy to essentially absorb or make or dissociate various bonds in order to increase the rate of the reactions. And you can see that in these contexts, we can think of reactions that may be electrochemical reactions as well as chemical reactions. Basically, the basic principle can be very similar, utilizing electronic structure surface binding to weaken internal interactions to facilitate rate of the reactions. So one can say that these are would be correlation, right? Correlation we know is not causation. So the question will be, can we learn more about what are the active sites and how the active sites may turn over as function of voltage or as function of operating conditions? And in this regard, to probe really the elementary reaction processes and defining what might be the active sites, and we leverage electrochemistry of single crystals as well as in situ characterization, utilizing synchrotron coupled with density functional theory. So we utilize in situ surface X-ray, so really glancing angle X-ray. We take X-ray only from essentially X-ray comes extremely shallow angle, so we diffract only the top surface layer, right? We look at the different rods. For example, if you look at the 001 rods that come from largely scattering from ruthenium as function of voltages of such a single crystal ruthenium dioxide, the 110, there's no change as expected. On the other hand, if we look at the 01L or 10L rods, this is coming from scattering largely from the oxygen. So if we have such a surface, typically we have two sites. We have a ruthenium cusp site and a bridge site. As the cusp site absorb water, as we increase the voltage, and then the water can gradually be oxidized or deprotonated from water to OH to O, and essentially at oxygen evolution potentials becoming this superoxide species. And this is something we can directly detect and probe and refine through the in situ surface X-ray diffraction measurements. We see essentially the reduction of the distance of the oxygen getting closer to the cusp site. On the other hand, for the bridge site, essentially the distance doesn't change very much, and we essentially see the site is oxygen terminated. And from such measurement, we can see the cusp is the active site, where a bridge is not involved in catalytic activity of oxygen evolution. We can couple this with DFT calculations to understand the limiting step at the 1.5 volts, where the reason we see this superoxide species is due to essentially the binding or stabilization of the proton on the nearby site. If we liberate and deprotonate this hydrogen, then we can essentially evolve and release the oxygen. And this step is relimiting. And so this is essentially is a one experiment, one example. We can see what is the energetic limiting step and what is really the active moiety before the oxygen evolution. We can also study different surfaces, right? And ask a question, are, let's say, all the cusp sites the same? Right. So for example, if you have 110, 100, and 101, you can see the cusp site is MO5. They're all very similar from the first coordination, but the second coordination, they are different. right? So we can also ask the question that using both combined DFT and synchrotron measurements to address, can the cut sites be different, right? And how the cut site might be different if they exhibit different activity. And we perform essentially measurements, and we note that if we have different cut sites, right, from 110 to 100 to 101, we gradually weakening all oxygenated species. Right, so for 100, we weakening the species so that the deprotonation of the superoxide species is such that we reduce the barrier, and so that 100 has much higher activity than the 110 surface. But if we further weaken all the species, then the prior step, the conversion of O to OOH, becomes really limiting, and then the catalytic activity of 101 is reduced. And our surface is no longer covered or by the superoxide species, but our surface is passivated by O-terminated surfaces. Right? So this essentially provide insights, not only toning the chemistry, but toning really the specific moiety or surface electronic structure are very important. Right? So essentially chemistry, right? You can tune really the electronic structure of individual oxygen, and toning the surface atomic structure. You can also tune the specific electronic structure of the oxygen. Right? So inspired of knowing oxygen is the active sites for oxygen evolution, we utilize machine learning methods, specifically graph convolution neural network, to predict the specific, really the local per site, per oxygen site, how they may correlate with binding or specific binding of oxygenated species. Right? So generally speaking, our work is looking at correlation of binding or average binding of oxygen or binding of species with oxygen sites for a given surface or for bulk. And now we are essentially looking at if we have a different structure, or if we look at substituted compounds, there will be many, many different oxygen environment. It depends on what metal neighbors they may have. And utilizing this method, we can go beyond just electronic structure. We can look at per site atomic vibrational frequency, look at per site oxygen p-band center, beta charge, as well as magnetic properties. And we can essentially look at, how these different electronic structure may influence the binding of various species. And more importantly, what we learned is if you look at the electronic structure influence on these three reaction intermediates, let's say O or OH or OOH, they have very different dependence. And this will also suggest that if you only just tune one electronic structure descriptor, we cannot really optimize these three essentially reaction intermediates, right? So require essentially different type of active oxygen sites in order to optimize the catalytic activity. And so this is essentially one idea that we want to essentially increase the environment or local environment of oxygen to fine-tune further tune the catalytic activity. And to this regard, we have recently developed a hybrid inorganic catalyst. And so this is basically an idea. We have a metal hydroxide layer. So this layer, these MO6 that bond either they connect with each other by either corner or edges, and these layers connected by organic linker. So either through the organic linker or through substitution in the metal layer, we can tune essentially the binding of, let's say, the oxygen site. That can catalyze OER. For example, we can look at these nickel substituted catalyst, where if we substitute a different, let's say, a lanthanum, yttrium, zinc, or aluminum or iron into the nickel site, we can change it. We can change the nickel redox potential. Right? So if we make the redox potential more positive, that means it's more difficult to oxidize nickel site. And that translates to the binding of oxygenated species, OH, will be weaker. And that's correlated with increasing OER activity on such a surface. Right. So this is essentially just really a beginning of increasing different, environment for the oxygen through organic and inorganic hybrid. So I want to take maybe a stop or check with Abraham. We have gone roughly 30 minutes, and I want to stop and see if we want to end here and address questions. If you want me to continue, I can speak a little bit on lithium-ion batteries, in particular, how to relate the same thinking, how the oxygen in the, let's say, positive electrode may influence the stability of the electrolyte and the cycle life of lithium-ion batteries.
Please continue.
Great. So lithium-ion batteries and electrolytes plays a very critical role. Not only influence, the ion transport, we influence really the electrochemical potential or the lithium redox for either electrodes on the absolute energy scale. The electron transfer at the interfaces would influence the power and the energy of such a system, and the stability and interface would influence also the power, the lifetime, and safety of such batteries. And we would like to, advocate the electrolyte is a key enabler in order to commercialize new chemistry, new materials, and in lithium-ion and sodium-ion beyond, as well as other chemistry such as metal, lithium metal batteries, and air or sulfur batteries. Right. For example, we have electrolyte, known electrolyte that can stabilize graphite. So we have lithium-ion batteries, and for the past decade, we have been dealing with, the challenges of gradually increasing nickel to increase the energy density of lithium-ion. But this is typically associated with degradation of life, cycle life, and degradation, also the safety. And this has to do with the instability of carbonate electrolytes towards a high nickel positive electrode. And today, we don't have a viable, stable electrolyte against metal and nor against the oxygen electrode. So therefore, we don't have a commercial or practical use of such batteries. And this is something that I want to advocate. This is a very exciting area to develop new electrolytes, to improve our understanding of electrolytes, so we can improve not only a known system, but able to advocate and transform and develop new technologies with higher power and higher energy and a longer lifetime. So looking at the challenges of, let's say, nickel-rich positive electrode material, and as we increase nickel to, let's say, nickel NMC 811, the degradation of or cycle life of such batteries, it would decrease significantly relative to NMC 811. And over the past decade or so, we've been working utilizing combination of techniques, in-situ measurement, DFT, connecting really the concept in catalysis applied to battery interfaces. And then we developed the following understanding and explain why the known carbonated electrolyte degrades on nickel surfaces. Right. So essentially, we have carbonate electrolytes or carbonate solvents. They can be activated. We have CH bond activation on surface oxygen side of nickel-rich oxide. And the CH bond activation on surface oxygen, right? So upon absorption, would dissociate another hydrogen on the nearby oxygen side. And this hydrogen becomes a proton and simultaneously reduce the nickel or the transition metal on the surface. And having a protic species, essentially we can have a generation of HF with anions, and then this would lead to a dissolution of the transition metal and generation of passivating organic films that build impedance. And so this is directly supported through in situ FTIR measurements, right? So if you look at the EC alone and with NMC 811, upon charging, even at very low voltages, 3.8, 3.9 volt at the beginning of the charge, where we can see we have increased the signals at wave number higher than what we expect for the carbonyl groups in EC. And this can be explained by the generation of VC or generation of dehydrogenated EC molecules supported by DFT calculations on the right. Right. So this is direct evidence to show that at beginning of charge, without generation of molecular oxygen, without generation of singlet oxygen, that electrolyte can be degraded. And once we generate these dehydrogenated species, we can generate essentially acidic species that can lead to dissolution, and we have essentially formation of organic fragment on the surface and increased impedance. And if we change it NMC to 811 to 111, we see no change in degradation of the carbonate species. And we can explain this degradation or predict what surfaces might be able to do the spontaneous dissociation of a carbonate solvent by relating the hydrogen absorption strength to the oxygen p-band center, or more generally, the ligand p-band center relative to Fermi level. Right, so if you look at nickel dioxide, it has very high driving force for dissociated absorption of carbonate or absorption of hydrogen. 2 EV translate 200 kilojoule per mole. On the other hand, if you have fluoride, cobalt fluoride, and nickel fluoride, basically there is no thermodynamic driving force. And this can be utilized to explain the phenomena in the literature, what surfaces people have used and find success, as well as can be used to predict new surfaces to develop a more surface stable NMC or nickel-rich compound. And utilizing this design principle, we can coat a surface with a little bit of fluorine that can lead to degradation, a diminishing of degradation of NMC 811 in a conventional electrolyte. So this is toning of the surfaces that we can make it essentially prevent the oxygen site to activate CH bond of the carbonate, right? And to prevent degradation and generate a protic species. On the other hand, we can also test the hypothesis to say, now, what if we utilize, maintain these active oxygen site on the surface, but we change our electrolyte, and by developing molecules that can essentially be more resistant to oxidative dehydrogenation. And this is really leveraging our work with Jeremiah Johnson over the past 7 years in developing electrolytes for lithium oxygen batteries, right? We want to develop liquid electrolyte or solvents that can be stable against superoxide, peroxide species. And so we develop a framework how to think about molecules and stability of the molecules bond by bond. And we look at the computation experimentally, look at their stability against hydrogen removal, proton removal, bond by bond, as well as stability against nucleophilic attack and electrochemical oxidation. And we find, for example, the sulfur-amide-based electrolyte, we have fewer hydrogen relative to our conventional carbonate electrolyte. With these hydrogen here, they're much more resistant to oxidative dehydrogenation. And these molecules can essentially survive the test of excess peroxide, superoxide at 80 degrees C for 3 days without degradation using NMR examination. We can utilize, such a solvent and test them against NMC 811. And you can see that such a solvent with a similar molecular structure with the salt lithium FSI. right? And both molecular structures, essentially free of oxygen, may be free of hydrogen, may be subject to oxidative dehydrogenation. And we see much improved stability relative to a carbonate solvent. And such a solvent has also shown to be stable against lithium cobalt oxide, can be cycled to 4.7 volt without degradation, right? Where a conventional electrolyte would also not be able to support a high charge of any late transition metal positive electrode, and due to essentially the high covalency of the high oxygen activity of these oxides. And we want to develop electrolytes be able to stable against these highly reactive oxygen, because we can utilize more of the lithium per transition metal oxide volume or weight. And so this is essentially one opportunity, one example of designing electrolyte based on fundamental understanding of the reactivity between the electrolyte and the surface. And similarly, we can also tackle the challenges of lithium metal reversibility or stability utilizing similar idea. Right. So, for example, if you see over the past few decades, if we change the liquid electrolytes, right, and the Coulombic efficiency of lithium shipping and plating can increase significantly, right, and up to maybe 99.5%, and approaching the possibility that liquid electrolytes may one day rival also the stability or the possibility of developing pure lithium metal batteries enabled by solid state or ceramic electrolytes. And utilizing electrolytes, particularly utilizing the redox power of lithium, the thermodynamic redox potential toned by the solvation environment of the solvent, the solvation environment as influenced by the salt. We can essentially tone the redox potential of lithium by up to 0.5 or 0.6 volt. And this essentially would change the thermodynamics and kinetics of reduction of the solvent, reduction of anions that can form, for example, very different SEIs, either organic or inorganic SEIs, which underlying essentially the stability of lithium shipping and plating and influence the morphology. Right. So essentially, our current thinking that if you have an electrolyte that controlling the right reduction of organic solvent and anions, developing a more inorganic passivating layer, one can render a higher efficiency. Not only this is really important, I just want to end this talk to say that there are a large number of research groups also using lithium and utilize lithium to mediate the electrochemical reduction of nitrogen, right? So essentially we use lithium to as a reducing agent to be able to bind and dissociate with nitrogen, and then once we have lithium nitride, we have a protic source, let's say ethanol, and on the surface we can generate ammonia. The structure of SEI, the solid electrolyte interface, or the electrolyte can play a very important role in shaping the SEI, where that can influence the Coulombic efficiency of ammonia, or the conversion of nitrogen to ammonia at this interface. So to end, I just want to show this particular result. For example, if we change a different electrolyte, right? So let's say different lithium anions, different concentration of the of lithium ion in the electrolyte, we can change on the thermodynamic, on the vacuum scale. On a solvent-independent reference, lithium redox potential can be tuned by, let's say, 0.6 volt, and you can also see the Faraday efficiency can be increased significantly as we change the redox potential. And this has to do, we believe, through in situ Raman measurements that we form a more pronounce the lithium fluoride, and we form more pronounced reaction intermediates, such as lithium alkoxide as a reaction intermediates, and a more crystalline of lithium nitride. Right. So this is, what I want to end is that electrolyte is a very important essential gradient to see all future innovation of battery technologies. So very exciting area. Encourage everyone to learn and get involved. So therefore, to innovate, to develop a new electrolyte formulation, it is very critical. And in the past, also 5 or 6 years, we've been working with a group of researchers, both experimental computation, been developing automated experiments, high throughput experimentation, making different formulation of liquid polymer electrolytes, high throughput machine learning, high throughput molecular dynamics, essentially to develop more understanding as well as faster formulations in order to expand our compositional space and libraries of electrolytes to enhance our learning as well as the performance. So with that, I just want to thank you for your attention and acknowledge the folks whom I have the privilege to work with, students, postdoc, collaborators in the area of catalysis, as well as the students, postdoc, collaborators in the area of batteries. So thank you so much for your attention.